yes, an angle is formed by rotating a ray about its initial point or its vertex. So what I'm going to do on this coordinate plane over here is I'm going to create an angle. I am going to have my initial ray, or my initial side as it's called, be on the positive x-axis, and I'm going to rotate this ray about the origin. The distance between those two rays is our angle measure. And angle measures, angles, are normally denoted with theta, most famously, but any lowercase Greek letter will work, or uppercase capital letter. So you'll see theta, you'll see alpha, beta, you'll see a capital A, capital B, capital C. It does not matter. All of these refer to angles. Now this down here is our initial side. It's where the angle started. And where the angle ends, where the ray ended up, is called our terminal side. Terminal meaning end. And the point where the two rays meet is our vertex. Hopefully you're very familiar with angles. Like half of geometry was about angles. Not half, maybe not half. A lot of geometry. All right. So now, just really quickly, if we're starting from our initial side and going towards our terminal side, and we are going counterclockwise, this produces a positive angle. So this first little example drawn here for alpha, this will give us a positive angle. Versus the second example for beta there, because we're going clockwise, we're going to have a negative angle. And the last one, do you think that's a positive or a negative angle? That gamma is a positive because we are going counterclockwise. But we do know it's an angle bigger than what? 360. Why do we know it's bigger than 360? It goes more than once around a circle. Now, just really quickly, these next two examples, the one on the left, is that a positive or a negative angle? Positive, and the one on the right is negative. Yes, because we're going clockwise. Now, sometimes angles are drawn in what is called standard position. Now, all that this means is that our initial side is where? Where does it look like our initial side is on both of these? The positive x-axis. Anytime our initial side is on the positive x-axis, we can say that the angle is in standard position. It's just a vocabulary word that applies to some of the angles we'll be dealing with. Do angles always need to start on the positive x-axis? No. Some do, and they're referred to as standard position angles. And then, what unit do we normally measure angles in? Degrees. How else can we measure angles? Radians. This entire unit, we will not be touching radians. We're only dealing with degrees this unit. Next unit, when we learn about the unit circle, we will definitely be using radians. This unit, we're using degrees, and most importantly, when knowing we're dealing with degrees, is making sure that your calculator is what? In degree mode. So your calculators, or if you're borrowing one of mine, the newer calculators will tell you at the top what mode it's in. It'll either say radian or degree. Now, if your calculator does not say this, it's fine, just like mine. What you do is you go to second mode. Oh no, that's quit. You just hit mode, go down to radian, over to degree, and press enter. Now you can hit, yes, exactly. Now you can hit second mode to get out of here. It's heartbreaking to me when you're going to solve these huge word problems. And I mean, there's going to be a lot of steps to these word problems. Some of the word problems I'm going to solve for you take me 20 minutes to explain at the end of this unit. So it's heartbreaking that you do all of this beautiful work and you get the problem wrong because you were in the wrong mode. You need to make sure you're in degree mode. Okay. So let's practice drawing our standard position angles. Before we draw the 135 degree angle, I do want to review, how do we number our quadrants in math? Yes. You number them in a C shape. I always think of a C. Ah, yes, and it's going counterclockwise, just like our standard position positive angles are counterclockwise. So this right here is quadrant 1, quadrant 2, quadrant 3, and quadrant 4. We number in a C formation. Now, this positive x-axis, if I have my initial and terminal side on the positive x-axis, it means that my angle is 0 degrees. How many degrees would the angle be that lies on the positive y-axis? 90. What about the negative x? And what about the negative y? And then what if you go all the way around back to 0? How many degrees is that? 360. So, whereabouts is the 135 degree standard position angle? Where is its terminal side? In the second quadrant, about where? How do you know it's halfway?
Halfway between 145 and 135.
Yes. We know that 135 is past the 90 degree angle. So in your head, if you take 90 degrees away from 135, you get 45. 45 is always going to be halfway between each one of your quadrants. So my terminal angle, my terminal side here is halfway between 180 and 90. So my angle is 135. Now what about part B, that negative 60 degree angle? What quadrant is that going to be in?
Fourth.
The fourth quadrant, good. About where? Yes. So we know that we can split each quadrant into two parts, knowing that each part would be 45 degrees. We can also split each quadrant into three parts, knowing each of the three parts is worth how much? 30. So 60 is 2 parts of 3 through the fourth quadrant. So I'm going to go not 1/3, but 2/3 in the negative direction. Does it have to be 100% accurate when you're drawing these lines? No. But it's good to visualize about where they would be. I'll never be sitting here with a protractor and be like, oh, Gio did not draw 60 degrees. He drew negative 59. He gets a point off. Okay, what about 270? Where's that going to be? On the negative y-axis, going counterclockwise. Not normally. Like, it's up to you. Most times I don't, but because we're consciously trying to figure out counterclockwise and clockwise, I am. Now, where is the 495 degree angle? Ah, how did you get that? Yes. We know that 495 is more than a full circle. So if we subtract 360, we get 135. And guess what? We've already drawn that angle on part A. We know where it is. But instead of just going from my positive x to my terminal side, I need to go around and then back to my terminal side. This is a 495 degree angle. Yes. Any questions here on how we drew these standard position angles? So now we're going to learn about what is called a reference angle and reference triangle. A reference angle is the acute. Now, what does acute mean? Small, less than what? Less than 90 degrees. So it is the acute angle formed by the terminal side of our angle, wherever it is, and the x-axis. So here, our terminal side on part A is here. What is the angle between the terminal side, the acute angle between the terminal side and the x-axis? 45. That is our reference angle. Now, if I was trying to apply trig to this problem, obviously we're not being asked to solve for anything here, but say I was being asked to solve for something. Trig, when we're using trig, what does trig need in order to solve something? An angle and a sides of what? A triangle. We need a triangle. So I'm going to create what is called a reference triangle. You create a reference triangle by making sure that your reference angle is in it, which it is, great. And also by drawing a line perpendicular with the x-axis. This is a reference triangle. It's always including a line perpendicular to the x-axis. Now look at part B. Is 120 a reference angle? No, it is not acute. What do you think the reference angle is in this problem? We want an angle with the terminal side and the x-axis. 60. How do we get that? 180 minus 120 gives us 60. So our reference angle here is 60 degrees. Reference angles are never negative. You're not considering them to be negative. It's just the angle we're using for reference in this problem. And then I create my reference triangle by drawing a line from my terminal side perpendicular to my x-axis. On part C, what is our reference angle? How did you get that? Yes. 210, take away 180 because we know the first two quadrants add up to 180. 210 take away 180 gives us 30 degrees. So here our reference angle is 30 degrees. And I have that reference triangle. And lastly, what do you think our reference angle is in part D? And how did you get that? 360 minus 315 gives us 45. We also could have done 315. No, well, yeah, no, I would have done 360 minus 315. Any questions so far? Honestly, all of this has been vocab. We haven't done any of the solving yet. All of this, I guess, could also be termed pre-knowledge before we actually apply trig. Okay. So now, just really quickly, when we are setting up trig ratios, as they are called, a trig ratio is just a side length compared to another side length. So here, if I'm trying to find the ratio of mx to am, what do I get? Which simplifies to 1/2. I have found the ratio comparing those two sides. What about WL over WE? 5 over 10, which simplifies to? These two numbers being the same. And we were comparing the exact same position sides, means that these two triangles are what? Not congruent. They're not the same size. They're similar triangles. Because the ratio of side lengths are the same. They are proportionate. So now, before we set up our trig ratios, we do need to recall when I'm thinking about my angle, which in this case is theta, where the adjacent side is, where the opposite side is, and where the hypotenuse is. So on this triangle, let's start with the easy one. Where is the hypotenuse? The diagonal that's across from the right angle. Where is the opposite side? BC, across from the theta. And where's the adjacent side? The one that is right next to theta, the one that's touching theta. If something is adjacent to something else, it means it's right next to it. And of course, when I'm labeling my triangles, I don't write these full words out. I just label with H, O, and A. H, O, and A.
So how do you know which one's opposite?
Opposite is not touching your angle, but the adjacent side is the side touching your angle. You see that? No, this is our angle. Don't, the right angle is never the angle we're referring to. Okay, so now let's practice using sine. Sine is always the ratio of the opposite side over the hypotenuse. So, in this example 4, we're trying to find the sine of 30. That 1 centimeter side, what side length is that? Our H, O, or A? Opposite. What is the 2 centimeters? H. Adjacent doesn't have anything. So if I'm trying to find the sine of 30, sine is O over H. What is my ratio? 1 over 2. And this is actually the most famous trig ratio. The sine of 30 is always 1/2. Hey, Kate. And it does say check this using your calculator. Our calculator's in degree modes, and then we just hit sine of 30, and it will always give us 0.5 or 1/2. So we're actually going to skip example 5. We're going to come back. I'm going to create a totally different problem here. Okay, that's the problem I'm going to create, because I realized there was a type of problem that wasn't in this packet, so I definitely need to make sure that we do this problem. We'll get to it. We're not quite there yet. And I'll give you time to copy this down when we get to this problem. Before you look at any of those trig ratios, how do you remember how to set up your trig ratios? What is the thing going through your brain when you hear trig? SOHCAHTOA. It is like the most famous thing associated with trig. So, maybe your teacher taught you, what was the, I forget. It's like some old horse caught another horse taking oats away? No. It should have been in geometry, yes. SOHCAHTOA. What SOHCAHTOA does is it helps you set up your trig ratios. So what it means is, and we just actually worked with the SO, it means that sine is opposite over hypotenuse. See how it's O and then H? It means that it's opposite over hypotenuse. Whereas the C stands for cosine. Cosine is A over H, adjacent over hypotenuse. And TOA, the T stands for tangent, is O over A, or opposite over adjacent. So all that SOHCAHTOA does is helps you set up those ratios, helps you know what each trig function is equal to. Does anyone know what the heck those 3 other trig functions are? They're not the inverse. Inverse of sine is just this. Yes, so this one right here, SEC stands for secant. CSC stands for cosecant. And COT stands for cotangent. Now, These are our what are called reciprocal functions. Why do you think they're called reciprocal functions? What do you notice? Oh my goodness. They're just the reciprocals of the original three. So cosecant is the reciprocal of which one? No. Sine. See how it's h over o? That's the reciprocal of o over h. So cosecant is the reciprocal of sine. What is secant the reciprocal of? Cosine. And what is cotangent the reciprocal of? Now, I know this is confusing because you're like, okay, sine and cosecant are reciprocals. You would think that the s's would go together and the c's would go together, but no, it's opposite. The one that starts with an S goes to the one that starts with a C, and the one that starts with a C goes to the one that starts with an S. Or at least that's how I remember. Because they're reciprocals and they tried to flip too much. They tried to flip too many things. And they can't, right, they can't say, oh, the reciprocal of sine is cosine. We already have a cosine. So they had to come up with a different word. Yeah, it's confusing. Don't try to logic your way through it. Now, we're not really going to get too much into the usefulness of the reciprocal functions in precal. The usefulness for reciprocal functions is way better explained in calculus when you're trying to find things like the derivatives of the original trig functions. So we are going to be using these functions so that you'll be better prepared for calculus, but we're not really in-depthly using them, if that makes sense. We're much more using the three originals. Okay, so let's start doing it. Let's try one. On this example 6, what is our adjacent side if that green angle down there is our theta? 3 is adjacent, right? It's the side touching our angle. What's our opposite side? 4. And what's our hypotenuse? And how did you get that? Oh, it's a Pythagorean triple. But if you're not very good at memorizing Pythagorean triples, what can you do to solve? The Pythagorean theorem. Where if we're solving for the hypotenuse, it's always the square root of a squared plus b squared. So that's 9 plus 16, which is 25, and the square root of 25 is 5. You are going to get so sick of using the Pythagorean theorem. Oh boy, I hope you're not sick of it already. Oh no. Okay, so now we're going to set up these trig ratios. I hate to say it, but personally I hate this type of problem, where they're asking you to set up all 6 trig ratios. Does anyone have an inkling as to why I might hate this? What's the point of this? What are we trying to do actually in this problem? Practice so that we can solve for what here in this problem? In the end. The angle. How many trig ratios do you think we need to solve for the angle? 1. And yet they make us solve for all 6 because they're like, oh, they need more practice doing this. Oh, I hate that. Extra practice just for extra practice. It's annoying to me. So, let's practice. How do we create the sine ratio? What goes over what? Right. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. And tangent is opposite over adjacent. So katoa. So sine is opposite over hypotenuse. Opposite is 4, hypotenuse is 5. What about cosine? Adjacent over hypotenuse, so what is it? 3 over 5. And tangent is what?
4 over 3.
Yes. OA. O over A. 4 over 3. Now, actually, I don't really mind the reciprocal functions in this case because what do we have to do? Oh my gosh, just flip the original. So what does cosecant give us? 5/4. What does secant give us? 5/3. And what does cotangent give us? Boom, I'm done. Any questions on how we set this up? All right. Sometimes they'll ask us to go the other way. Instead of giving us a triangle, they will give us one of the trig ratios and ask us to find the other 5, which again, I hate this because why do we need to do it? Go ahead. Just more practice. So, what do you need if you're confused on what the 1 and 3 represent? What do you think you should try to do first? Always in precal, always in geometry, when you're confused, what should you do? Draw. Oh, draw the picture. Go ahead and draw a triangle. Any right triangle, it doesn't matter as long as it's a right triangle. And I'm going to put theta in one of the empty angles, not the right angle. Now here, sine, we know, is what over what? Opposite over hypotenuse. So where on my triangle should I put a 1? On the right side. That's my opposite. Where should I put the 3? On the hypotenuse. And what do you think we now need to do? Solve for the adjacent using a squared plus b squared equals c squared. Now, I don't know why, but anytime we're solving for a leg, I always assume we're solving for b. It does not matter whether you solve for a or b. I just gravitate towards b. B is going to be your c squared minus your a squared square rooted. And what is 3 squared minus 1 squared? Square root of 8. And what do you think we need to do? Good. It's going to be 2 root 2. That is our adjacent side. So, cosine gives us what ratio? A over h, so 2 square root 2 over 3. What about tangent? Ah, yeah, you're right. What do you notice? Ah, you got to do the thing. Get the square root out of the denominator by multiplying by the square root over the square root. So here we get the square root of 2 over 2 remains in front, and then the square root of 2 times the square root of 2 gives us how much? And in total, this whole thing is other way around. Square root of 2 over 4. Yes. Now cosecant. What do you get for cosecant? 3. What about for cosine? Oh, you got to do it again. Oh my. So square root of 2 over square root of 2. We get 3 square root 2 over 2 times 2, which is 4. Now, when you are finding the reciprocal of something that you've already rationalized, do you think you should flip the rationalized version or the original version? If you flip the original, you don't have to worry about rationalizing. But if you flip the rationalized version, meaning you have 4 over square root 2, you'd have to rationalize again. So instead, whenever you're flipping to get your reciprocal, always flip the original. It'll make your life easier. Any questions on how we solve this problem? And yes, your Math Excel is going to consist of a lot of these tonight for homework. All right. Last type of setup problem they're going to give you. Now I'm going to change this first theta to be an alpha. Suppose alpha, guys, I have 3 more problems I have to get through, so suppose alpha is the measure of an angle in standard position with the point -3,7 on the terminal side of the angle. Use the reference angle to determine the exact values of the 6 trigonometric functions of theta. Now, because it told me that this angle is in standard position, and also it gave me a point on the terminal side, I know that I'm going to have to draw a coordinate plane, where my terminal side is created by the point -3,7. Doesn't have to be perfect, just has to be about where -3,7 would be. And I create an angle based on that point. Where alpha is the measure of the angle from the positive x to our terminal side. Now I cannot create a triangle using the angle alpha. Instead, how would I create a triangle here? You create a theta that is actually a what? Starts with an R, yes. It's our reference angle, and then how do I create my reference triangle? This is why we practice creating the reference angle and reference triangle, because we need a right triangle in order to find these side lengths and find this angle. The point gives you the side lengths, right? -3,7 means that the bottom length on that triangle is how much? -3. And the 7 means that the side length is how much? But because we're trying to find all of the 6 trig ratios, which I hate, we really don't need to do this because we already have 2 side lengths, but because we're trying to find all 6, guess what we have to solve for? The C length, which we get by doing -3 squared plus 7 squared square rooted, which gives us 9 plus 7 squared, which gives us 58, which actually cannot be simplified. So, which one of these numbers is our opposite side? 7. What's our adjacent? And what's the hypotenuse?
58.
So, what is our sine ratio? 7 over square root of 58, which becomes what? Yes. 7 root 58 over 58. What about cosine? Oh. -3 over square root of 58. Yes, which we multiply by the square root of 58 over the square root of 58. And we get negative 3 square root 58 over 58. And tangent's easy. This is actually the trig function you should have used if you were just trying to solve for this angle. What is the tangent of theta equal to? Negative 7/3, yes. What is cosecant? Square root of 58 over 7. Notice how I flipped the original. It made my life easier. What is secant? Negative square root of 58 over 3. And what's cotangent? Negative 3/7. So again, if they had really asked you to solve this problem, instead of having this last sentence, they had said, find the angle alpha, you would have just used tangent of theta, solve for theta, but then what would you have had to have done? If we solve for theta, is that our final answer? How would we get alpha? Subtract it from 180. Good, good, good. Now, just really quickly, what do you think the inverse of sine times sine is going to give you here? 30. What happens when we take the inverse of the original? They cancel, they're opposites, they're inverses. So here it's just asking they are inverse functions. Okay. So now, I'm so sorry that I've been just going, but these are there's so much to these notes. I'm sorry. Your brain's probably fried and you're like, please stop. But I just have to get through everything. I'm so sorry. I know, we've done so much, and I'm not done.
Oh, what?
Go back to that problem I said we need to skip.
Yay.
We're now actually going to be solving for side length and angle measures. So first we're going to solve for x. Now, which trig function should we use if we're solving for x? Yes, because we're given the side length of 7 and we're trying to find the opposite side. So we have to ask ourselves, based on SOHCAHTOA, which one uses O and A? Tangent, where tangent of theta is equal to O over A. How big is our angle in this problem? 30. What's our opposite side? X. And what's our adjacent side? How would I go about solving for x? Right. What do we do to get x by itself? Multiply each side by 7. So x equals 7 times tangent of 30. Now is when we finally pull out our calculators. 7 tan 30. And we get 4.041. I'm in degree. We're also going to have to solve for y. Now, which trig function do you think we should use if we're solving for y this time? Cosine, a over h. Cosine of theta is a over h. Our theta here is 30. Our adjacent side is 7, and our hypotenuse is the y. How do we get the y by itself?
Just do 7 cosine 30. 7
times cosine 30? Divided by. Good. Whenever you're trying to solve for something in the denominator, I like to think of it as you're switching what it's equal to. So y here is going to equal 7 over cosine 30. And we get 8.083. This is what you drilled and killed in geometry, if you remember. If not, it's okay, I just showed you. But this is what you did so much in geometry, so hopefully it's ringing a little bell here. Yeah. Oh, so this was the very last unit before COVID hit, by the way. I've got one more problem, Geo. I've got one more problem, I see you. I know. Listen, we can do it. One more problem. I have to remind you how to find angle measures. So we just found side lengths. Now we have to know how to find angle measures. On this problem, x is our theta. What is 23? Oh, it's our hypotenuse. What's 11? What trig function will I use here? Cosine of theta is a over h. Now I'm trying to solve for my theta here this time. My x value is theta. How do I do it? Yes, but do you ever actually hit divide by cosine? Instead, yes, we take the inverse of cosine on both sides. So all we have to do in our calculator is hit second cosine of 11 divided by 23. And we get 61.428. But this is an angle, so what does it need? A degree symbol. Any questions there? Yes, what's your question? Because we have an H and an A, the only one that includes H and A is cosine.